cumulative final exam. It's just exam number 4. But it will take the full period of time because we do have a bit of material to cover. It's Thursday. Finals like 4 to 6:45 or something. Whatever it says in the announcement is what it is. And I also put the link for the final schedule if you don't have that. So, unless instructors say otherwise, that's when your final should be, right? And I also put the material that'll be on there. So it's basically combined loading, stress strain transformation, beam deflection. And for this material, for the column buckling, I'll not put it explicitly as a required question on the exam, but I will add a column buckling extra credit problem, right? So don't expect it to be like worth an entire other exam or anything, right? So it's just going to be an extra credit on the one exam, okay? All right. So, all right. So let's get started on the buckling material. All right. Let me do all my multitude of clicks to get this to work. All right, so this is chapter 13. It's a column buckling. And so this is kind of a good example, right? I should have like the reveal on this. I shouldn't just give you the answer all at once. But so like let's say you're designing a stool, right? And so 400-pound downforce, that's a pretty reasonable force. I mean, that would be a heavy dynamic force from somebody who's even like 300 pounds, right? And so we're going to have a steel post, right? So there's an allowable stress there. And so your job is to design this post. All right, so what do we know? Well, the stress in the post is the force over the area, right? And we know that stress must be less than the allowable stress, right? And so here's a 40 KSI allowable stress. That's a pretty reasonable stress for aluminum, actually. And if we go through that and we figure out what the diameter should be, we need a post diameter of 0.112 inches. Okay, so that is less than 1/8 of an inch. So what do you think would happen if you designed if you saw in the store a stool with an 1/8 inch diameter post? Would you think that would be a reasonable solution?
Definitely not.
Why? But it's okay. So why? I mean, obviously, yeah, it would look pretty comical, I think, right? I mean, I think there's no doubt about that. So what do you think would happen? It's not going to fail in compression, right?
Maybe in bending, it'll bend.
You're close. I think you're close, right? When you say bending, yeah, but there is no, I guess you're saying like if there were some lateral loads on this, right? Like set laterally, right?
But yeah, maybe if the person is like moving around a little.
Right. You have a bending issue with that too, right? Yep, that is true. But even let's say you somehow didn't have that, right? And you were just to sit straight down on this. I know that's kind of a ridiculous concept for a chair, but do you think you would sit on you think the 1/8 diameter post would hold your weight? Or 400 pounds, something that's your weight. So yeah, in fact, it won't, right? And the phenomena we see here is what we call buckling, okay? And the way this would fail is in buckling. This is a failure phenomena that really limits the operating loads. It has a significant effect on how much load a structure can maintain. So while a 1/8 inch aluminum post can hold in compression 400 pounds without much issue, the buckling load is an order of magnitude lower. And it only happens in compression. And you've seen this phenomena before. So I don't know if you can see. Can I see my camera? I don't know if you can see my camera, right? So this is a wood dowel, right? Can you see it? Again, this is
Yes, sir.
Yes, sir, we can see it.
live, right? So, I'm just putting a force on axially, trying to compress it, right? And what is it wants to deform like it is in bending, right? It doesn't compress like we would expect it on P on A, right? P on A compression, you'd expect the length to change because every little element compresses down, right? But in fact, if I put a force on it, you can't tell, but I'm slightly increasing the force, and then that's buckling out of the page. And then it jumps down, right? So this is a buckling phenomenon. The post has buckled. And I mean, obviously, that term from layman's parlance, and that's what it means, okay? But this is the issue that we're going to talk about here. So again, obviously something like this is clearly a buckling phenomena, but there are other structures that you might not consider this to happen, all right? And you have to be careful of this, okay? So here you can see some pictures of some rather catastrophic results of a buckling failure, okay? So even anytime you have a structure where you have parts of your truss are under compression, that element may in fact buckle, all right? Here is a bridge that failed. It's due to buckling, but the buckling happened because there was a slight twisting of the bridge. And so we're going to talk only about compressive buckling, but bending and torsion can induce their own buckling loads that'll make the structure fail at significantly lower loads than you would think if there wasn't a buckling failure, okay? Here is an example of a storage container that failed under a compressive load, but you can see the buckling mode has a twisting or torsional aspect to it. And then you've all seen this concept of how to make a aluminum can fail under compression, right? And that is a rather complex buckling mode. These are all types of buckling. And what we're going to talk about is basically column buckling, which actually can be extended to a lot of these cases. This case, and even to a degree, these cases, the first mode of buckling is a compressive load that we can treat with this column buckling model, okay? So that's the critical thing. When it does fail, it has large deformation. You lose the ability to support any load at all. And this is what you see in these pictures. And the load, when it can happen, is significantly lower than the other typical design loads in compression or torsion, okay? Okay. I mean, not always, but I mean, this is what we see here. So this is why it can be a particularly problematic issue, okay? All right, so how can we look at this? All right, well, this is a very simple way of thinking about it. And this is not a bad example because it does give you an idea about like exactly how this is fundamentally different than other types of failures we've seen. This is actually what we mathematically call an eigenvalue failure, but we'll show it here. So here we've got this pin structure, right? We have the, you can assume that these are rigid in comparison to the stiffness of the spring, okay? So we're going to assume that those two links are fully rigid, and the only thing that allows the structure to comply is this spring here. And so obviously, as this pivot link moves in, compresses the spring, this point will deform downward, okay? All right. And the way this happens is only from this top load here, P. So if we draw the free body diagram at this pinned location right here, okay, we have this restorative force from the spring, okay? So that's like the lateral spring force. So that's going to equal the spring constant times how much the spring deflects. And so we're going to call this distance here delta. That's the deflection. And if you look at this triangle, that deflection is going to be L on 2 sine theta, right? All right. So that's the restorative force due to the spring. Actually, I'll put a little S here just to make sure that it's denoted to the spring. All right. What balances that? Well, you have the force, you have this link here where you have the down force P. Obviously, that puts the element into compression, right? P cosine theta. And then that gives you a net force in the X direction. So that force due to P is going to be P tan theta. So we have the force in the X direction from the load, and that's going to be P tan theta. And we see two of those because we have the force from the link of the top and the bottom. So I'm going to put a 2 there. All right. So if this is an equilibrium, they're balanced. All right. And that gives us KL on 2 sine of theta equals 2P tangent theta. All right. And now if we consider small angles, because this is, for most structures, this is a small angle. And the concept of this spring, I should mention, this really is a simplified model of the fact that the beam or the column has a transverse stiffness, like the stiffness due to bending. Does that make sense? Right? So it's just an easier way to deal with it mathematically. So if we deal with small angle, then sine of theta would go to theta, and the tangent of theta also goes to theta. So they actually cancel out. And for equilibrium, we see that we get KL on 4 equals the load P. All right. And so that seems like a really simple relationship. But let's stop for a second and let's think about it. This is actually significantly different than the deflections we've talked about in the past. If you're just compressing a spring, like when we had axial case, right? If we put P on the x-axis and then the deflection on the y-axis, we had the deflection is PL on AE, right? Imagine this is for, right, the case of a column just, compressive on an axial member, right? This response is a straight line response, and the slope here is going to be AE on L, right? That's the spring stiffness of that column. But that means that if you look at this type of response, if you give me the load P, if you tell me how much force there is on P, you get a different equilibrium displacement, okay? So that makes sense. The displacement is linearly proportional to the load. In this case, that does not happen. The deflection, right? Theta is what measures the deflection. It's that angle, correct? In the equilibrium equation, that angle doesn't exist at all. It's disappeared completely. And what that means is there is only one load that you can see equilibrium at, where the force is exactly equal to KL on 4. There is no equilibrium unless the force equals the spring stiffness times the length of the element over 4. So that is like fundamentally different than when we see other types of deflections, right? This either it exists or it doesn't exist. And you can't consider different loads. If you have a system with a where L is given and K is given, right? There is only one force that you can apply downward where, you know, we're in this equilibrium position here. So what does that really mean, right? What does that mean? It's what we call a bifurcated type of solution. So one way you can think about it is if we were to look at this and we were to look at this plot. And so what I'm going to do here is let's take equilibrium. So again, I have KL on 2 sine of theta. And I'm going to just divide by P for now. And I'm going to divide by 2P, right? So this equation, before I did the small angle, I'm going to write like this. All right. So all I didn't do small angle yet. And I just divided by 2P, right? So if we put on the x-axis theta, okay. And now I know we've lost a little bit, but this quantity here, right? This is related to the force that gets transmitted through the link from P. And this term here is related to the spring stiffness, the force due to the spring, right? All right. So here's what we have here. This plot here in blue, this is the plot of Fx. This is the tan theta plot. And you can see here at 90 degrees, pi over 2, it's singular, right? This here is the plot of Fs. This is the KL on 4P sine theta plot. Right here where they intersect, that is the equilibrium solution. All right? That is the solution that we basically get from here. But it can only exist at a particular force, P. All right? Now, if we consider deflections less than this equilibrium theta, right? So when we had the buckled column, right? We haven't gotten the load up to that value. What happens here, right? The spring force is higher than the force, you know, transmitted from the external load. So the spring force has the ability to push you back, right? It's got more reserve. When we go beyond here, when we go to this region where the theta becomes greater, the spring force is not sufficient. And then the force due to the tan theta component becomes really big and the deflection goes to infinity. That's what happens. So we have this one equilibrium position here. And on this side, we have stable deformation. And on this side, we have unstable. So what that means is this solution, when P equals KL on 4, is what we call a critical force. And if you look at the buckling on my camera, right? As I increase the force, nothing happens. because the spring is able to push that node A back in line. Once I hit the force equal to this critical value, it bifurcates, and it always wants to do it out of the screen, and it bends significantly out of the plane, right? That is the critical buckling load. Now, mathematically, there is some stiffness post buckling if you keep it nonlinear, but when we linearized it, when we use small theta, that buckling load technically goes to infinity. So technically, if the small angle didn't get violated, this would deform out to infinity, right? But obviously, as it starts to deform significantly, theta is not zero, right? So this is fundamentally a different way of thinking things. Either it buckles or it doesn't. It only has a critical value. So basically, in this case, we have critical buckling at the value of KL on 4. If the load is less than that, we don't have buckling. If the load is greater than that, it buckles and it fails. So, it's either one or the other in this sense, okay? Maybe it fails in compression before buckling or after, right? Or there's other failure modes that might happen before the buckling load, but one limit on this load is going to be that critical buckling load. And it's not like it deforms a little bit and then it fails, right? It's nothing. Then when we hit the critical load, it actually buckles, the thing swings out, and then it technically deforms out to infinity. Okay. So we have this critical phenomena, right? The buckling load is like a bifurcation. Like if we were to practically plot force deflection for this beam case, if we were to take this case here and we were to plot force deflection, or let me use theta here, because theta basically is a measure of the deflection, right? And this is the force P. What would happen is, as we increase the load, there is no deflection angle theta until we hit the critical value, the KL on 4, and then the deflection becomes infinite. I don't know why I did that. Okay, so this curve would just plot out like that. That's the linearized solution. Practically, actually what happens for nonlinear buckling is something like that curve. So it initially goes quite a bit out, but there is some ability due to nonlinearity that you can support some post-buckling behavior, okay? So that's what we're talking about, all right? Now you can do the math on this, and I won't go through the derivation, but I don't even know if it's in the book because it involves the eigenvalue problem of basically the fourth order beam bending problem. But for a column, and this is why I say this stuff is pretty plug and chug, for a column that is pinned at both ends, the critical buckling load is given as follows. So if the load is greater than pi squared times Young's modulus of the column times the I, that's the same I we used in beam bending, over the length squared. If it's greater than that, it will buckle. If it's less than that, it will not buckle. So that's the buckling load that it fails at, right? All right. So like I said, pretty easy to do these problems. The only thing that we change a little bit is we do not always have pinned conditions. Sometimes we have a column that looks more like this. Maybe it's fixed at both ends. And here the buckling load is different. Or possibly it might look something like this. It might be free at one end and fixed at another end, okay? So those are all different end conditions. And in that case, we get a different critical buckling load. But fortunately, there is a nice trick to this. And you can see it here, okay? So this is our prototype case right here. This is where the critical buckling load is pi squared EI on L squared. All right. Now let's just, for example, look at this case where it's fixed at the base, but free at the top end. So this would be like the bar stool, right? Or the stool, right? So if you look at this closely, you might say, okay, look, if I were to reflect that about the fixed point, this curve here, this looks like the pinned case. This case here. The only difference is the effective length is different. Like this would be the pinned pin case for a length twice as much. All right. So we can actually get these other cases by talking about the effective length. All right. So really, we want to talk about buckling as follows. Right, where we're going to use the effective length squared on the bottom. And if we have pinned pin, the actual length is equal to the effective length. If we have fixed free, the effective length is twice the actual length, and that's what you would put in here to get the critical load. If we have fixed, this case, right? Here, the effective length is half of the actual length. That's what you would put into this equation. And you could also have, this is the pinned at one end, fixed at another end. We call that guided, fixed sometimes. And here, the effective length is 0.7 of the actual length. So in this equation, the other way you see that is here. We have these correction coefficients, K, where the effective length is actually equal to K times the actual length. And you can use that in this equation. So it's really the same difference. You can either use the effective length or you could use the effect, you can use this equation and use K times L, where K is the correction factor for the end condition, okay? And so now you can take this Euler buckling and extend it to other end conditions. That's pretty much it. That's all we're going to do in this chapter, okay? That's it. So that's what I mean. You will not get problems like, okay, when does the soda can buckle? Or how does this bridge buckle? Okay, but you will be able to solve a variety of problems for buckling of the column, right? And we'll do the stool in the next slide. But you could also imagine, like, if you had a truss, right? Let me draw a truss here, simple truss. I don't have a big space here to draw. I guess this is easy. Let's say you had a truss like this. And you have a downforce here, and it's roller. So some of these elements are in compression, okay? And you could look at, for a truss, we typically consider this to be pinned and pinned. We consider it to be this case. So technically, if you have a truss and the elements are slender, even though the compressive load might not cause it to fail due to the axial failure, you really need to check that each one of those elements in compression does not fail due to buckling. If one of those fails due to buckling, the whole thing kicks out in much similar way that this oil rig failed, okay? But again, that's pretty easy to do. It's just the same problem here, right? This problem here, but applied to each compressive element in the truss. If the element is in tension, if the internal force is positive, right, you don't have to worry about buckling. You know, there's no buckling in tension. It's only in compression. Okay. All right. So if we wanted to revisit the stool example, okay, so here we can consider the stool fixed at the bottom and free at the top. So in this case, the effective length is 2L, or we can use K equals 2, right? And so we're going to use the fact that the critical buckling load is pi squared EI over L effective squared. So, okay, so we have the Young's modulus of 30 KSI. So we have steel. So it's a steel post. The length is, let's say, 36 inches. Now, again, you know, for compression failure, the length doesn't enter into it. For buckling, it does. So that means my effective length is 6 feet or 72 inches. We use K equal to 2. All right. And then we're going to put in, you know, we're going to use that diameter of 1/8, right? All right. That was the one that for just P on A would have supported 400 pounds, right? Obviously, we get I and all that stuff. And now we plug it into the buckling equation. So now instead of that 1/8 inch post supporting 400 pounds, because of buckling, it can't even support half of a pound. All right. So this is what I mean when I say, you know, calculating the buckling loads is pretty straightforward, but in this case, it has a major impact on the stability of this structure, right? So we've gone from being able to support 400 pounds from like P over A calculation down to supporting less than a half of a pound because of buckling, okay? So it's pretty significant, all right? So it's significant.
Professor.
Yeah.
So for example, what if you change the diameter? What if you give it a bigger J, for example?
Right. So we do that in the next one. So
Okay.
so you could do this. So you could do this from a design standpoint, right? So let's look at this. Let's look at this equation, right? So let's say you wanted to, obviously you don't want it to buckle and you want to hold 400 pounds, right? So P is fixed. It's going to be made out of steel. So E is fixed. I'm going to assume the length is fixed, right? Because you want the stool of a certain height. Although clearly the length has a huge effect because it's length squared, right? Making the length less will increase our critical load. So the only thing we have to fool around with is I. So yeah, you could figure out what I you need so that it doesn't buckle under a load of 400 pounds. And then from that, you could figure out the diameter. Does that make sense? So that would be like the design problem. And
Okay.
that's what happens on the next slide. So turns out you actually don't need too much more diameter, but you do need about 3/8 of an inch diameter. Okay. And that will not buckle. All right. Better yet, I think would still be to do a hollow section. Okay. But also again, as was pointed out earlier, right, that, you know, when somebody does sit down or is on a stool, they push back on it and things like that. So there will also be lateral loads. So it won't fail in bending, but you might be not a big fan of the amount of deformation you might get in bending. Okay. All right. But that's how you would use this in the design problem. Okay. All right. I think that's all I got for the slides. So let's do an example. Let's close this out. Let's stop sharing.
Which is why a hollow shaft again?
Oh, because, well, remember,
Yeah, from the past.
you always are gonna. It's I. It's the same I for bending. So putting the material out farther is always better. So whether it's making a bigger J for torsion or a bigger I for bending, that's what you want to do, okay? So, all right. You use, for the same amount of material, you'll get a much higher I. And so you'll increase both the stiffness of the chair, so when it does bend due to lateral loads, and you'll also significantly increase the buckling load, okay? And normally, you know, I think, you
Okay.
know,
Thank you.
so I use the chair because I think it's something physically we can imagine, you know, sitting on a 1/4. I mean, I think still if you made a chair with a 3/8 diameter post, right? I still think you would have a bit of an issue, but that's mostly again for the sort of the side loads, right? Okay. Okay. Yeah, let me get a problem. Let's do a problem. Like I said, the biggest thing that you need to know about this is that buckling exists. It's got to be in your, you know, in your mind when you design these structures, because it has such a dramatic effect. So if you're designing a truss-like structure and some of those elements are under compression, you know, not only do you have to check the P on A failure stress, that those stresses are less than the allowable, as we've done in the past, you really need to also check that those forces are less than the buckling forces, okay? Which you never did in statics, and we haven't done in this class previously, but you do need to do that. Unfortunately, sometimes this is at the end of the class, and sometimes time runs out and people don't cover it. But and those students, who knows, they might design horrifically buckled designs in their life, but you will not, because you've seen this. Like I said, for a straight up column, it's easy to see, but for things like trusses and whatnot, it might not be so easy to see. So let's do a simple one. Let's do, I mean, this is almost so simple. We could do 313, but this is so plug and chug. Let's just do it. Let me try to do this a bit more. I'll do one that's a little more interesting than this, but let's see again. Well, you know what? I'm not gonna do this one. This one's stupid. This one is too simple. We'll do one that's more. I was gonna do just the pin case, but that is just kind of ridiculous. I think you guys can do that. Let's do one that's not so good. Okay, let's do this one. All right. All right, so now you should see the problem, right? 318, right? So we're gonna do problem 318. All right, so here we have a column. It's a wide flange I-beam column, W1250, and it's made out of ANSI 992 steel, right? So, okay, so steel means that Young's modulus is 30 times 10 to the 6th psi. And since we know it's a W1250 beam, we can look that up again in the same table I think we did last time, right? In the back of your book, I think it's Appendix C. Let me go pull it up. And so you can look up I directly from there. And I'm going to do that right now, maybe. Right. It's Appendix B, I'm sorry. So from Appendix B, we can get that I equals 1250. It's 394 inches to the fourth. All right, so that's given from there. Okay, so here they want us to find what is the load P that this column can support without it buckling, okay? All right. So first thing we want to do is we know we're going to have the critical buckling equation, right? So it's the pi squared EI over L effective squared, okay? Or if you want to, you can use, in terms of L effective, K times the length, okay? So the first thing we need to do is we need to identify what are the end conditions here. So what would be the end conditions for this type of loading? If you want to, I don't know if you have the book in front of you or the ebook in front of you.
Would it be fixed ends?
Right, it's fixed on both ends. Yeah, and where you would see the table is, let's see, where is it? In your book. Right, where is it? Oh, here it is. Right, in the textbook, it's figure 1310. That shows you the different end conditions, right? So this is fixed, or fixed both ends, right? And in that case, from figure 313, right, L effective is half of the actual length, or K is equal to 1/2. It gives you the same answer, right? And then if we're going to put that into here, right? So let's put that into here. So that gives us the critical buckling load is equal to pi squared. E is 30 times 10 to the 6 psi. I is the 394 inches to the fourth. And now we're going to have to use the effective length squared, right? So we're going to use K equals 1/2. And then the length is 20 feet, but right, we need to change this to inches. So it's going to be 20 times 12 inches, and we're going to square all that, right? So in this case, let me ask you this. Does the buckling, in comparison to pinned, is the buckling load greater when it's fixed than pinned, or less? Well, I get the calculator going.
I think it's going to be greater.
Yeah, it's going to be greater, right? Because length is in the denominator. The effective length has become smaller. So yeah, it's going to be able to support more load, right? So actually, like, the worst condition is free, right? Then pinned and then fixed. But yeah, you know, if you have like pinned, fixed, and all that sort of stuff, it can be a mix of those, all right? So let me do this. Pi squared 36 times So we get 1/16 to the 9th above, but downstairs is going to be big. So that's 6 times 20 is 100. So the effective length here, right, is 120 inches. Okay. And then if we square that and divide, I get a critical buckling load equal to 8 times 10 to the 6th pounds. So it's a pretty high load, right? So if the buckling load there were to exceed that, we would get failure, but due to it buckling, okay? Just for the heck of it, let's see what the P over A failure load would be. So, right, in that case, we just need to know the area of this, which again, we can get from that Appendix B. So for a wide flange 12 by 50 beam, the cross-sectional area is equal to 14.7 inches squared. And well, let's see what it would be, right? So if we had the critical load, the compressive stress would equal that critical load over the cross-sectional area. So it would be 8. And what would that give us as a stress? All right. So that gives us a stress of 544 KSI, not KSI, sorry, KSI. All right. So that's actually a pretty high stress. Most structural steels actually would probably fail at that stress. So in this case, right, you would probably see failure due to the P on A stress before you saw failure due to buckling, right? But I mean, again, you know, it depends upon the actual grade of steel. You'll notice in here, when you compute the buckling load, the strength of the material doesn't enter into it at all, which again is kind of unusual, right? So the stiffness of the material does enter into it because we have E and I, but the strength doesn't enter into it, right? When we figure out the P on A stress, obviously the allowable stress enters into this, okay? And usually, you know, for most steels, like, well, you know, I take that back. You know, you can find some steels that are about 100,000 psi. You know what I mean, right? So, yeah, it's a little bit. You can, I mean, you can find something maybe like. Right, but that means that, you know, before you got to compression, you would actually have before you get to buckling, you would have a compressive stress that would actually cause failure. All right. Now that doesn't have to necessarily be the case, right? If we had a smaller I, right, you know, that would be the way it is. Okay. All right. Honestly, it's a little tricky to find problems that are that challenging, but maybe I will do. Oh, that one's not bad. Should we do this one? Yeah, I'll do this one. This one's pretty simple too, but this is an example of considering it on a truss structure. But I think this is not so bad. to clear this. All right. All right, so let's look at this problem. This is 313 in the text. So here we have a structure made of two pinned links, AB and AC. And then they give you the force applied here of P. And they want you to know, they're asking, what's the maximum load P that the frame can support so we do not get buckling, okay? Now from this, it's pretty obvious that element AC will only see tension, but AB will see compression, and therefore we have to worry about a buckling load on it, okay? All right, so let's look at this, from a loading standpoint, right? So we need to figure out the force that's effectively in element AB, and it's not P, okay? So this is a class example. You don't just plug P in, you don't get just P critical, pi squared EI over L squared, right? Like this is not the answer, okay? All right. Due to an external force P, there's going to be a certain amount of load here that's in compression, okay? So we need to find the force that's in element AB from P, okay? That's what's going to cause the buckling, all right? All right, so we're going to do some statics, all right? So what's the easiest way to do this? And I guess we just do method of joints, right? Method of joints. And so if we draw the free body diagram at point A, right? Here we have the force P, okay? Then acting up, I'm going to assume it's in compression. We have the force from element AB. I'm going to do it that way. And then we have the force in element AC, right? And again, if you draw them, the arrows go in the other direction, it really doesn't cause any problem. This is a 3, 4, 5 triangle, as every problem in all these books are, but mostly in life they are not. So there you go. And so here, let's do sum of forces in the X and the Y direction, and we can get this to work out, right? So if we do sum of forces in the X direction, we get P has to equal FAC times 3 over 5, right? Or in other words, we can get FAC equals 5/3 P. And then we do sum of forces in the Y direction, right? This is sum of forces in the X. If we do sum of forces in the Y direction, we would get FAB equals 4/5 FAC. And we know FAC is 5/3 of P. So if we put that into here, that's going to tell us that FAB is 4/3 P. So the force, the compressive force in element AB is equal to 4/3 of the value P. All right. Okay. So let's figure out the critical buckling load now for AB. So let's kind of go a little bit to the side. So here's the critical buckling load for a column AB, right? So here, pi squared I'm going to assume what E is steel, right? Okay, they give you 200 GPa, right? E is 200 to the 9th pascals, right? We can figure out I from this. So the I of this shape, I is going to equal pi over 64. Okay, so now here's the question, right? Which I should we use, right? We know that, I'm sorry, we know that I is base height cubed over 12. So should we use the I for bending around the x-axis or I for bending around the y-axis? Which I should we use? You got two choices.
The x-axis.
Okay, you're saying that let's do the I for bending around the x-axis. So that's the I about the x-axis. That's where the base is 50 millimeters and the height is, height is 100 millimeters, right? The other one, the I about the y-axis, in that case, the base is 100 millimeters and the H is 50 millimeters, right? Which one's going to be bigger, IX or IY?
IX.
That's right, because it's H cubed, right?
Yes.
So IX is definitely going to be greater. So if this were to buckle, in which plane would it buckle first? The one with the bigger eye or the one with the smaller eye? Maybe
The
another
one
way.
with the smaller eye.
Yeah, the smaller eye, right? I guess the better way to say it is which one will give you a lower critical buckling value, right? Since the eye is upstairs, the one with the smaller eye will give you a smaller buckle load. And that makes sense, right? It's going to buckle first in this direction because that's the direction that has less stiffness. Does that make sense? There actually is a critical buckling load for buckling in this direction, but it's going to be greater than in the other direction. So we need to use the smaller of the two eyes, that one, okay? That's going to give us the worst case. So we need to use, in that one, let me just slide this around. Cubed. So we need to use I about the Y, right? We use IY, and that one is going to be 0.1 meters times 0.05 meters cubed over 12, and that gives me an I of 1.04 to the minus 6th meters to the 4th, okay? And so that goes here. And then downstairs we have the length. Now this is pinned at both ends. So the effective length is the actual length, right? So it's the 6 meters squared, right? So you don't have to adjust that. If, let's say, we're fixed down here at the bottom, right, and not pinned, then we would have to use the K effective for pinned fixed, which is like 0.7, right? But that's not the case here. Okay, so we can get a number off of this. All right, so this gives me a value of 57 kips. Okay, 57,000 pounds of compressive force in AB is going to cause it to buckle. Okay, but that's this is basically that's the force AB. All right. So now we want to know actually what, that's not the force we apply. The force applied is P. So how do we get that? Well, we know that just from this relationship that P is equal to 3/4 of that internal force. And so what we're going to put into here is the critical buckling load for that, right? That's the one where AB fails. So this is going to tell me that this will fail. The structure will fail when the force P is greater than 3/4 of the 57 kips. And that is 42.7. All right. So that's when it would actually fail. That's when it would actually fail due to buckling. And, you could probably look at the stresses and the other elements. And, depending upon the slenderness of these elements, it might fail sooner due to like force over area type of failure, the tensor failure, right? So, like whenever you see structures that are in compression and they're slender, you know what I mean, right? Like that should immediately, like a light bulb should go off in your head and you say, look, I got to worry about buckling. Okay. So you have to go through all your other analyses. Does it fail due to bending? What's the combined loading stress in it? All that sort of stuff. Then is the load in that element less than the buckling load? Okay. And so if it passes all the other stress calculations, but the load is greater than the buckling load, well, then it's going to fail first in buckling. If it passes the other ones and then the load is less than the buckling load, then you're good. Okay. And that's kind of the way you have to go into doing this stuff. So usually we don't design to buckling, except like, if you have some really exceptional cases, right? But most of the time, the way we do this sort of stuff is you're going to design your structure for axial loading, torsional loading, bending, right? You're going to design it for that combined loading like we did in chapter 8, I believe. Well, whatever it is, the combined loading chapter, right? Now you've got a design, okay? Then if you have elements that are in compression, you really need to go back afterwards and check, do they buckle? I mean, that's typically the workflow for designing these types of things, okay? You usually don't design to buckle, all right? Okay. I think that's pretty much it because, it's kind of hard to, there aren't too many more interesting problems off of this, unless you start getting into energy methods and all that sort of stuff, which we will not do in this class. I should, before we go, I should mention that we will not cover it explicitly, but let me just mention it again. And actually, it's in 13.7 of your text. If you have a column, like let's say we have a column like this, and you apply a force P, and then if you have the same column, same E, same I, same L, same N conditions, but for some reason, the force is applied a little bit outboard of the neutral axis. There is some eccentricity, E. In this particular case, the critical buckling load for this case, I'll call this eccentric, right, is going to be less than the P critical for the non-eccentric case. This is peak critical, right? And it's just because there's an additional moment. So that's if you do, I'm not going to cover it, but you should be aware of that fact. Also, a lot of what drives this is very often we have imperfections, and they can really drive this stuff. It's almost this. It's very similar to like a stress concentration. Okay, and that's the way it is. Okay, all right. Yeah, another classic example of buckling, and this is, I can talk about this because actually we kind of just went through it this week. So one of the research projects we have is designing a lunar lander for NASA, and we have propellant tanks that hold liquid oxygen and liquid methane. So let's say this is the liquid methane tank. And to keep them liquid, they're under pretty high pressure. So these see about 400 PSI internal. And you guys know how to do this, right? So we got a pressure vessel. We were looking at making this out of titanium, a titanium welded spherical pressure vessel. And they went through and did the, allowable stress, the actual stress, which is the pressure, I always forget what it is, pressure times the diameter over the thickness, twice the thickness, right? Right, that one, right? They went through this calculation that we talked about in the combined loading chapter for pressure vessels, and they got a wall thickness. So I should mention again, this diameter here was about 3 feet in diameter. Okay, it's about a 3-foot diameter tank, and that came about because we have to hold a certain amount of propellant, right? Okay, and this thickness came out to be 20 thousandths of an inch. This has to fly, so we were very concerned about keeping the weight down. So that seemed pretty reasonable, right? This actually was a pretty good weight, and it holds the pressure. All right. Does anybody have an idea about what would be problematic about having a tank that is 3 feet in diameter, but only 20 thousandths of an inch thick wall? So a piece of paper is about 5 thousandths of an inch. Okay. So imagine taking a piece of paper and folding it in half and folding it in half again. That's about the wall thickness of this 3-foot diameter tank. Maybe it's a
I don't know, probably if something hits it, it will break very easily.
Yeah. Would it break though? What do you think about breaking? Think about it, right? It's not going to break, right? What'll happen?
I probably, well, the thing that is inside, it could get out,
No, but I mean, so 20 thousandths of an inch, actually, a credit card, this credit card, like this is Amazon card. That's actually, I just measured it. It's 30 thousandths of an inch. So it's less than that, right? So, okay, 3-foot diameter, right? That's about 3-foot diameter, right? And about this thick. What do you think would happen if you drop a wrench on it?
It would definitely bend.
And explode.
Well,
Maybe have a leak.
it might explode if you breach it, right? But it'll definitely dent, correct?
Yes.
Right? And that is a buckling mode. Okay, that is a buckling mode. Another one we have to consider is actually these tanks, the way they're configured is it looks like a snowman. We have 3 tanks. It really does look like a snowman because down below we have the liquid oxygen tank, and then we have the liquid methane tank. And then we have a very high pressure helium tank that pressurizes these guys. So it looks like a snowman. In fact, We call it the snowman design. And so these tanks will see the compressive forces of the tanks above them. Okay. And so buckling should definitely be a consideration here. Now, when this buckles, it's not going to buckle like the column, but it's going to buckle like the soda can. Does that make sense? But that's the same phenomenon. Okay, that's the same buckling load. All right. Okay. Well, that's all that's going to be covered in this chapter. Thursday, I'll just take questions on any problems that you want to do for the final. So again, look over the announcement I sent, but basically combined loading, transformation of stress and strain, beam bending, as well as buckling. But remember, buckling will just be an extra credit problem. Okay. All right. Oh, also, I've got the exams graded. I haven't released them yet because I'm just double checking them with the TA, but we'll put those out as well. And so you can do request regrades and all that sort of stuff through till I'll take regrades on all those through till the basically till graduation. Okay.